Today we are going to learn about efficient TensorFlow tensor manipulation techniques. We'll explore how to reshape, split, and concatenate tensors, mastering skills essential for data preprocessing and model training.
Welcome to our session on efficient TensorFlow tensor manipulation techniques. In the world of machine learning, handling data efficiently is crucial. Tensors, the core data structure in TensorFlow, allow us to perform a variety of operations needed for data preprocessing. Today, we'll delve into reshaping, splitting, concatenating, and more, equipping you with practical skills to enhance your machine learning projects. Our focus is on understanding how to manipulate tensors to prepare them for model training. By the end of this session, you'll be able to handle complex data structures with ease, making your data preprocessing tasks more efficient and effective.
Tensors are essentially multidimensional arrays, and understanding their shapes and dimensions is fundamental to manipulating them effectively. A tensor's shape describes the size of each dimension, and its rank, or number of dimensions, determines the complexity of the data it can handle. For example, a rank 1 tensor is a vector, while a rank 2 tensor is a matrix. Recognizing the shape of a tensor is crucial for ensuring compatibility in operations such as matrix multiplications or data reshaping. Visualizing tensor structures helps in grasping their dimensionality and how data is stored and accessed. This understanding is the backbone of any tensor manipulation, as it guides how we reshape, split, or combine data effectively.
Reshaping tensors is a crucial operation that allows us to change the shape of a tensor without altering its data. This is done using the tf.reshape function in TensorFlow. Reshaping is often necessary to make tensors compatible for specific operations or model inputs. For instance, flattening a tensor before feeding it into a dense layer or reshaping image data for convolutional layers. It's vital to maintain data integrity during reshaping, ensuring the total number of elements remains constant. Common scenarios include converting a 3D tensor to 2D or expanding dimensions for batch processing. Practical examples include reshaping a tensor to combine or split dimensions, enabling more complex operations and model architectures.
In machine learning tasks, splitting and merging datasets efficiently is essential for data manipulation. TensorFlow provides tf.split and tf.concat functions to facilitate these operations. Splitting a dataset is often required for creating training, validation, and test sets, or breaking down a large dataset into manageable parts. The tf.split function allows you to partition a tensor along a specified dimension, while tf.concat merges multiple tensors along a specified axis. It's crucial to handle varied data types and ensure the dimensions match when concatenating tensors. An example would be splitting a dataset of images and labels, processing them separately, and then merging them back for model training. These operations are fundamental for organizing data in a way that optimizes model performance.
Transposing and permuting dimensions are powerful techniques that allow us to reorder the axes of a tensor. The tf.transpose function in TensorFlow enables you to swap the dimensions of a tensor, which can be critical for making data compatible with different model architectures. For example, changing the order of dimensions in image data to match the expected input shape of a neural network layer. Permuting dimensions can also improve performance by aligning data with memory layouts that optimize computation speed. Practical applications include transposing a tensor for batch processing or aligning data formats between different libraries. Understanding how to effectively transpose and permute dimensions is essential for making tensors fit seamlessly into various machine learning workflows.
Adding and clipping are techniques used to ensure uniformity and consistency in tensor sizes. Adding involves adding extra data, usually zeros, to a tensor to match a desired shape, using the tf.pad function. This is particularly useful when processing sequences of varying lengths, such as text or time series data, ensuring all inputs have the same size for batch processing. Clipping involves restricting tensor values within a specified range, using tf.clip_by_value, to prevent extreme values from skewing results. This is crucial in scenarios like normalizing input data or preventing overflow errors. Real-world use cases include padding sequences for recurrent neural networks or clipping gradients during training to stabilize updates. Mastering these techniques ensures data uniformity and enhances model performance.
Broadcasting is a powerful concept that allows TensorFlow to perform operations on tensors of different shapes by automatically expanding dimensions. This is particularly useful when applying element-wise operations, such as addition or multiplication, between tensors. TensorFlow's automatic broadcasting simplifies computations and reduces the need for explicit reshaping. It's crucial to understand how broadcasting works to handle mismatched dimensions effectively and avoid unexpected results. For instance, adding a scalar to a matrix involves broadcasting the scalar across all elements of the matrix. Practical examples include scaling data by a constant or combining feature maps in convolutional neural networks. Mastering broadcasting strategies enables efficient manipulation of tensors, enhancing the performance and flexibility of your machine learning models. Sparse tensors are a specialized data structure that store only non-zero elements, reducing memory usage and computation time for certain types of data. These are particularly beneficial when dealing with large datasets that contain many zero values, such as text data or large-scale recommender systems. TensorFlow provides support for creating and manipulating sparse tensors, allowing for efficient storage and operations. You can create sparse tensors using tf.sparse_tensor and convert dense tensors to sparse using tf.sparse.from_dense. Understanding how to work with sparse tensors enables you to optimize memory and computational resources, enhancing the performance of your models. Applications include natural language processing tasks and graph-based machine learning algorithms, where data sparsity is common.
Applying tensor manipulation techniques effectively in real-world scenarios is key to optimizing machine learning workflows. In image processing, tensors are used to represent pixel data, allowing for operations such as data augmentation, where images are rotated, flipped, or scaled to enhance model training. In text data, tensors represent sequences of words or characters, enabling efficient processing and analysis through padding and embedding operations. Time series analysis benefits from tensor manipulation by reshaping data for temporal models and aligning sequences for batch processing. By mastering these techniques, you can optimize model inputs, ensuring data is in the ideal format for training, ultimately improving model accuracy and efficiency. Real-world examples highlight the versatility and power of tensor manipulation in diverse machine learning tasks.
As we conclude our session on efficient TensorFlow tensor manipulation techniques, we've explored a range of operations that are vital for data preprocessing and model training. From reshaping and splitting to transposing, padding, and broadcasting, each technique plays a crucial role in preparing data for machine learning tasks. Efficient tensor manipulation enhances model performance by ensuring data is in the optimal format for training. These skills are not only applicable to current projects but are also foundational for future learning and exploration in machine learning. We encourage you to continue experimenting with these techniques and applying them to real-world scenarios, as this is key to mastering TensorFlow and advancing your skills in data manipulation.